Hello all, welcome back to my video series on contiguous memory locations. So in the last video we have already discussed about contiguous memory allocation. In this series we will learn about the non-contiguous memory allocation. I know there is some issue with the spelling of contiguous. Okay, we'll correct it next, but let's see about what are the various non-contiguous memory allocation techniques. So first one is paging. Second is we already have discussed about multi-level paging, which is also one another type of paging technique. And third is inverted paging, which is also a type of paging only, but the technique is a little bit different from the previous two. Then we have segmentation, and at last we have segmented paging. So these are the non-contiguous memory allocation technique. So first of all, we will deal with all of these one by one. Okay. So yeah, in this series, we will learn about the contiguous memory allocation technique. So okay, let's correct it first. So the spelling will be Guous. Okay. Now it's corrected. Let's see about the paging. Okay, so in paging, let's see what is this paging is. So in paging, what happens that there is a mapping being done from the logical address to physical address. So we will learn about what is this logical address and what is this physical address. But till now, we know that physical address is the address of the program or the instruction in the main memory. So whatever we store in the main memory, whatever instruction or whatever things we have already stored, we identify them by a particular address, that is the physical address. But when we talk about paging, the another address comes into picture is the logical address, or also known as virtual address space. Okay, so what happens that uh, before talking about this, let's talk about how to represent the address. So first of all, if we talk about the logical address, or also known as virtual address, okay, so basically the logical address or is represented in the form of bits or byte. Definitely these are the two ways of representing, or it can be represented in the form of word. Okay, so either bit or byte or word, just like physical address we already have discussed in previous videos. So this logical address is also represented in the form of bit or byte or words. And for example, we can take it as it can be 512 kilobyte, or we can represent it as 512 kiloword. So when we say 512 kilobyte, then definitely we can assume it something like this, with some with the capacity of 500 kilobyte, and total number of rows is 2 raised to the power 9 into 2 raised to the power 10 is the total number of rows, and each row is carrying 1 byte of data. So there are altogether, if we divide it such a way, so 0 1 so on up to 2 raised to the power 19 minus 1 will be the total number of rows, and each row carrying 1 byte of data. Okay, now this is actually the logical address space. And if we talk about the logical address or LA, then it will be how much bits? 19 bits. So to represent all these 2 raised to the power 19 minus 1 row, we need 19 bits. So we have already discussed about how we get to this total number of bits to represent the number of rows. So we won't get into much detail. So this is all about logical address, and this is the logical address, and this is the logical address space, right? Similar way, we can have the physical address and the physical address space. So we already have discussed about physical address is the address of the instruction or data in the main memory. So in this we are talking about what is this physical address and physical address space. address space. So basically it is also represented in the form of byte or bits, you can say, or it can be represented in the form of words. For example, it will be 32 mega word, or it can be 32 megabyte. So when we say 32 mega word, that means 2 raised to the power 25 into one word. So 2 raised to the power 25 rows will be there, and each row width, that is each row data content, will be one word. So if you see like this in this way, so this is the memory structure. It will contain altogether 2 raised to the power 22 rows, like 0, 1, 2, up till 2 raised to the power 25 minus 1 rows, and each row carrying one word of data. Okay. So if we talk about the physical address, then number of bits required to represent the physical address is 25 bits, right? Why 25 bits? Because each address will be represented in the form of binary, and 2 bits are required, 25 bits are required to identify each address. Okay. Similar way for this also, we need 25 bits address, logical address, sorry, physical address will be of 25 bits, and it will also contain 2 raised to the power 25 rows, and each row will contain 1 byte of data. Okay. So this is all about the addressing scheme. Since when we talk about paging, the logical address or logical address comes into a picture. That is what we are going to discuss. So that's why I have first illustrated about do we address the how do we get into the addressing scheme. Okay. Let's say if we have logical address as 26 bit, and if someone asks about the logical address space, so logical address space is nothing but the capacity of the memory, uh, virtual memory. Actually, logical address refers to the virtual memory. We'll talk about it in some time. So this logical address space will be 2 raised to the power 26 into 1 byte or one word, depending upon whether it is a byte addressable memory or a word addressable memory. So it is something like uh, 2 raised to the power 6, that is 64 megabyte or 64 mega word. Okay. Similarly, if we have the logical address space given and it is 16 mega word, so definitely, if we need to calculate the logical address, so this will give us the total number of rows, that is 2 raised to the power 4 into 2 raised to the power 20. And this word is one word. Okay, I mean, this word is each row containing one word. So total number of rows will be 2 raised to the power 24. So logical address would be consisting of 24 bits, right? So we just have to look into this part, because this part will anyway give the row content, or you can simply say that it will give the width of each row. Okay. So that from the number of rows we can calculate the number of bits required to represent each row. And it is very simple. Like if you see that we have something we have, let's say, 4 rows. So if we want how many bits are used to represent each row, so if we represent in decimal number system, we represent like this: 1 2 3 4. But if we want to represent in binary, we have to represent like this. Okay. And this, so 2 bits are required to represent this 4 row. Okay. So from where this 2 bit came actually, so it came from this 2 raised to the power 2. So we are taking this power. Okay. So similar way we can conclude for logical addressing scheme. Now, let's say same for physical address also, it goes the same. Like if we have the physical address being represented by 38 bits, so if someone asks about what is the capacity, overall capacity, if it is a byte addressable memory, so 2 raised to the power 38, total number of rows into each row containing 1 byte of data. So it is equal to 256 gigabyte. Okay. And similar way, if we have been given like physical address space is 512 TB. So if someone asks about physical address, so it is 2 raised to the power 9 into 2 raised to the power 40. Okay, not byte. This is the number of rows. So altogether we need 49 bits of to represent this physical address space. So this is how we just go into the addressing scheme. Now let's talk about paging and let's talk about the logical address. So paging is basically a technique to map the CPU generated logical address to physical address. So it's a technique of mapping CPU generated logical address into physical address. Okay, so paging is the technique of mapping the CPU generated logical address into physical address, right? This is very important. Now, why the CPU not only just generates the physical address, that is the physical address of the instruction or the data? Why does it has to generate first the logical address and then the logical address has to be mapped to the physical address? So the CPU never generates directly this physical address. It just generates. CPU provides the logical address which gets converted into physical address, and conversion this mapping of this logical to physical address is done by paging. Okay, so this thing we will deal up in the virtual memory section. So it is going to come next, but in this section we are just dealing of the non-contiguous memory allocation. So we will just focus on that topic because this part, how does the CPU generates virtual memory address and why does it generates virtual memory, why not just physical memory address? So these all things comes under the virtual memory section. So here we are just discussing about the non-contiguous memory allocation techniques. So let's focus on to this. Okay. Now, so this mapping of logical address to physical address is done by paging, and paging is implemented at hardware level. Okay. Now, if the logical address is same as physical address, then no hardware support is required. Let's say if the CPU generates a logical address and that is equivalent to the physical address of the instruction, then definitely no mapping is required because even if you map, no as such paging is required. No hardware support is required for paging. Okay, no hardware support required. Right, but if the logical address and the physical address are different, let's say the CPU generates a logical address of 13 bits and let's say the physical address is of 12 bits. So definitely if it is logical address is not equal to physical address, then there is a need of paging to map this logical address into physical address, and hence hardware support is required. Okay. Now, let's assume the CPU has generated a logical address of 13-bit, right? And from this, we can assume that the logical address space will be 2 raised to the power 13. Let's say if the memory is word addressable. So 2 raised to the power 13 word, that is 8 kiloword. So the logical memory address space is 8 kiloword, and for that physical address is 12 bits. So we can say that the physical address space is 2 raised to the power 12, that is 4 kiloword. So the physical address is 4 kiloword while the logical address is 8 kiloword. So definitely the logical address space is larger than the physical address space. Okay. Now, let's draw the diagram of the how does the mapping occurs. So let's say we have this logical address space here, which is how much? 8 kiloword. So there will be altogether 8. Okay, let me just redraw it again because the diagram is a little bit not straight. This does happens when we are writing onto this board from the pen. So let me redraw it. Okay. So yeah. So let's draw the logical address space. So this is the logical address space and it is 8 kiloword. Okay. So this is 8 kiloword and it is divided into altogether 8k rows. Or let's say for this time assume that one row is consisting of 1 kilowatt occupancy. So it is consisting of 1 kilowatt, 1 kilowatt, 1 kilowatt. Instead of one word, we are assuming it is 1 kilowatt. So it can accommodate 1 kilowatt. So altogether we have 7 and this one is 8, 1 kilowatt. So now total number of rows will be 8. So if this is 0, 1, 2, 3, 4, 5, 6, 7. Okay. And it can in binary we can represent it like this with 3 bits. So 0, 0, 1 and 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. So this 8 kiloword consists of 8 rows, each row containing 1 kiloword of data. Okay. Now this one was about the logical address. Now we have the physical address space. So the physical address space is 4 kiloword. So let's say in this also we have 4 rows and each row containing 1 kiloword of data. Okay. So this is 1 kiloword of data in each row. And these are the 4 rows 0, 1, 2, 3. So 0, 0, 0, 1, 1, 0 and 1, 1. Okay. Now let's suppose what this is actually the physical address space and this is the logical address space. Now paging will do what? It will map this address into this address. So this is actually 3 bit address. This is 2-bit address right now. Just we are assuming actually it was 13 and 12, but just for the sake of as we are just assuming that it is 2-bit space and this is like this. Okay, why? Because we have taken that each section or each fragment I mean, each partition consists of 1 kiloword of space. Okay. So now this 1 kiloword refers to the page size. Okay. Or in terms of physical memory space, you can say it is as the frame size. Okay. And in virtual memory space context, you can term it as the page size. Okay. So now this 1 kilo word here and this 1 kilo word is the same actually. So at a time in the physical memory, we are just bringing some 4 pages from this, each consisting of 1 kiloword of data, right? So at any time in the physical memory we are just constituting of 4 pages, we are just bringing 4 pages from the virtual memory and putting it at some address like 000110 and 11, while if we see in the virtual address space it is at different location. It is at zeroth location. This one which is at first location in the physical memory, it is at the second location. This one is at the fourth location and this one is at the seventh location. So obviously this address is not same as this address. So what paging will do, it will map this because the CPU just generate this address. Okay, but CPU is not aware of this address, so the mapping of this will be done by paging. So we'll see next how this mapping is done. First let's talk about the term. So this 1 kiloword is the page size and this is called the page number. In terms of physical address space, this is called the frame number and this is called the frame size. So here page size is equal to the frame size, but the page number is not equal to the frame number. Okay, because this mapping will be done by paging technique. So, so we can say that logical address space, logical address space which is divided into equal size frame or is divided into equal size page, equal size page. And if we talk about the page size, so page size is 1 kilowatt. Page size is equal to 1 kilowatt, right? Then if someone asks how many pages are there, how many number of pages are there in the logical address space, so it will be logical address space divided upon 1 kilowatt, that is page size. That gives us the number of pages. Okay, same goes for physical address space. It is divided into equal size frames, and frame size is 1 kilowatt, so number of frames we can calculate as physical address space upon frame size. Okay, so we can write it as physical address space is divided into equal size frames. Okay, and frame size or page size is equal to frame size. Page size equal to frame size. Okay, and hence number of frames, if we ask number of frames, is equal to physical address space upon the frame size, right? Now at one instant of time, only some of the pages from logical address space, that is LAS, will be brought into PAS, will be brought into PAS. Okay, so in this way we can see that at one instant of time we have only some of the pages being present. Now what is this page actually? The space size which we have divided the physical and virtual memory into, the space size is nothing but it is a set of data, that is 1 kilowatt. So it is a set of instructions that is accumulated as one. So in equal size frame we have divided it. So let's say 1 kilo word, then this is 2 to power 10 into one word. So there will be altogether 2 raised to the power 10 minus 1 rows, and each row will containing be one word. So in this way we have divided the page size, right? So this is one page. So in a case of paging, we talk about pages that are being brought from the virtual memory to the main memory, and this page in terms of main memory it is termed as frame, and its size is same, that is the frame size is equal to the page size. Okay, so whenever this paging is applied, whenever we divide the virtual and physical memory into equal size page or frame, then paging comes into picture. So paging is applied on this, and when paging is applied, then there is a need to map the page frame number with the page number because both are different. So whenever paging is applied, page table has to be maintained. Page table has to be maintained. So what does this page table tells us? This page table tells us about the mapping between page number and frame number. So what frame contains what page, so that mapping comes into picture from this page number. Now to maintain this paging part, For each pages present in the physical virtual memory, we need to have a corresponding frame in which shows that where is this page present in the main memory. Okay, so like we have this page number named into 3, 4, 5, 6, and last is 7. So we have this for the page table, we have this as the page number. So this denotes the page number of the logical address space. Okay, and in that we will denote where which page is contained in which frame. Okay, so to see that, we will go back to this diagram where we have drawn this. Here if you see that we have bought, okay, just a second. So here we have bought this zeroth page into zeroth frame. So the zeroth page is present in zeroth frame. So we can write it like this, that zeroth page is present in zeroth frame. Okay, 00, right? Like 000, 001, 010, 011, 100, 101, 110, and 111. Right, so zeroth frame is present in zeroth frame. Zeroth page is present in zeroth frame. Now if we talk about another frame, that is the second uh, page. This is the second page, and this second page is present into, let's say, in first frame. Okay, so the second page is present into first frame. So we will write like in the second frame, we will write it as it is at the first page. So second page is present in first frame. Okay, for this first page we don't have any frames located, so we will keep it as blank. Now we will see next that this fourth page is present in second frame. Okay, so we will write it like this, that the fourth page is present in second frame. For third page we don't have any frames, so we will keep it as null. Then we'll come back and see that here the eighth frame, let's say seventh frame, is present into the third frame. Okay, seventh page is present into third frame. So we will write it here as third. Okay, these all are vacant because they are not assigned, these pages are not assigned to any frames, right? So this way we will put the frame entry actually. So this is the frame number. Okay, sorry, not frame number, this is the page number, and this is the frame number. Okay, so each page number is associated with a particular frame number, right? So this is also known as the page table entry. Okay, page table entry. So for each page, we provide the particular frame in which the page is present. So page table also known as the address translation table, because it translate the logical address to physical address. So page table also known as address translation table. Okay, and number of entries in the page table, okay, is equal to the number of pages in the LAS. Obviously for each page we need to assign a particular frame, we need to denote where is this page present. So number of entries in the page table is same as number of pages in the LAS. Number of pages in LAS, right? So this is important because for each page we are assigning any frame, or we are denoting it whether it is present in the main memory or not. If it is present, then we provide the page table entry as the frame number where this page is present. Otherwise we keep it as null. Okay, now the next thing comes up of the page table entry. So page table entry definitely contains the frame number. Page table entry contains the frame number. Contains frame number, right? And also one more thing is frame number, also known as translation bits. Frame number known as translation bits. So this is very important. If we talk about translation bits, then it definitely refers to the frame number. Okay, so this is all about how this conversion happens. So we'll see more about it in detail in the next lecture. How does the CPU generates the logical address and how it gets converted into physical address with the help of page table. So this we will see next in the upcoming videos. So keep watching, and if you do like and share and subscribe, if you do have any questions, please do comment in the comment section. So yep, thank you very much for watching, and keep watching the video. Thanks.